Hi, so today we are doing the module 3, chapter 1, class 12 physics. So far we have learnt about charges at rest, electrostatic force and field, and we learned about electric dipole and electric dipole moment. Electric dipole moment is represented by capital P, and then we learned about electric field axis at any point on the axis of dipole, that was equal to 2 kp upon x cube, where x is the distance from the center of the dipole to the point. And we learned about axis electric field at any point on the equatorial plane of an electric dipole, and E was minus kp upon x cube. So then we learned about electric dipole is kept in external electric field and it experiences a net force equal to 0, and next torque is equal to Pe sin theta, or vector product के रूप में P cross E. Or this P cross E has one more meaning. The direction of the torque can easily found by this formula. The direction of torque will be perpendicular to both dipole moment and electric field. The given external electric field. So today in the module 3 we are going to learn, suppose if the dipole is kept in a non-uniform electric field, where the electric field intensity varies from point to point. Different points the electric field intensity is different. Suppose there is a dipole and here the electric field intensity is E1 and E2, minus Q plus Q. So then the force is QE1 and the force on the second charge is positive Q charge is A2, and there is a net force, and the net force is not equal to 0 because E1 and E2 are not equal. So such a dipole will experience both torque and force, because torque was already there and here also torque will be there, and the net force is 0 in the uniform field, but in the non-uniform external electric field a dipole will experience both force and torque. Means it will rotate and also it will move. So it will rotate and move. Both type of translatory and rotatory, both type of motion will be present. So we go for the next topic, that is electric flex. And the symbol is phi. And the phi is a Greek symbol, Greek letter. And what do you mean by electric flex? Electric flex simply means the total number of field lines passing through a particular area. Suppose you have an area and a lot of field lines are penetrating through it, and less field lines will be penetrating, it means that the flex is less, and more number of field lines the intensity of electric field is much greater, means more number of field lines are penetrating through this. It means the electric flux is less. And numerically the flux is equal to the dot product of the electric field and the area, or we say EA cos theta, and the area is the area of the surface, whatever the shape of the surface is. It depends on three things: electric field intensity, area, and cos theta. I will explain you with an example. So suppose I have a surface, this is a surface. So there are electric field lines like this. And if I keep the surface, most of the electric field line will penetrate through this. But if I keep the surface like this, what will happen? Most of the field lines are going up and going down, and very less or no field line will penetrate. So that is the speciality of the cos theta here. So cos theta, cos 90 and cos 0. Cos 90 is 0 and cos 0 is equal to 1. That is a trigonometric value, of course, for 0 degree and 90 degree. So here electric field is a vector quantity, area is also a vector quantity. Normally we think that area has no direction, but even in mathematics area is considered to be a vector quantity. Reason, area has a particular direction, a plane has a particular direction. Even a plane is characterized by a particular direction. Even the equation of a plane, one of the main thing is the direction, and the direction is always perpendicular to the plane. If the plane is like this, then this will be the direction. Plane is direction, then this will be the direction. So a plane has a direction, area has a direction. So here, if the area is like this and the direction of area is this, so this is the area direction and this is the field direction, and an angle between this is what? 90. So cos 90 is what? 0. So entire flux will become what? 0 in this case. But in this case, the area is in this direction, perpendicular to the plane. So this is area. And electric field is also in the same direction. So theta is how much? 0 degree. So cos 0 is how much? 1. So you have maximum number of field lines passing through it. Maximum number of flux. You have maximum flux through this surface. So the flux depends on the intensity, because more number of field lines will be there. Electric field intensity, and the flux depends on area. More bigger the area is, more number of field lines will pass through. And cos theta, so the alignment of the surface. The surface is like this, very less number of field lines will pass through. The surface is like this, then more number of field lines will pass through. So that is why the flux clearly depends, even though it is a scalar quantity, it depends on three things here. Even the direction of the area. So by this even you can define electric field. What is electric field? If theta, you just keep it 1, then the electric field is what? Flux upon unit area. So the flux per unit area, how much electric field lines are moving through a particular 1 meter square area, a unit area, then that is actually electric field intensity. So there is another practical explanation of electric field intensity, but let's go with the flux. And there is a famous theorem called Gauss Law. Gauss Law states that for any charge enclosed by a surface, suppose I have a spherical surface or I have a cuboidal 3D figure, or in this cube or cuboid or sphere, a football-like structure or a room-like structure, inside if I keep a charge, then what the Gauss law says, the flux is equal to 1 upon epsilon naught times the charge enclosed by the surface. So the flux field lines, the field lines penetrating out or penetrating in, that's what, the net flux, the total flux through a 3D surface, through a closed surface. Anyway, surface is 2D, but the 2D surface, if it is closed, it becomes a 3D figure. So a closed surface and the flux and the flux passing through or penetrating through the surface is equal to 1 upon epsilon naught times, if inside is vacuum, then 1 upon epsilon naught times the Q enclosed, charge enclosed by the surface. So that is what the Gauss law is. And you can even prove this Gauss law, but the detailed proof is not given in your syllabus. So the main thing is the Gauss law statement, you have to by heart it. This Gauss law statement is 1 upon the flux, electric flux passing through a closed surface is equal to 1 upon epsilon naught times Q enclosed, charge enclosed by surface. But still I will give you a small arbitrary explanation for Gauss law. And suppose you have a spherical surface and you have a charge somewhere here inside, or otherwise, okay, charge somewhere here inside. And then what is a flux? Through penetrating out of this surface. And you already know what is the formula for flux. Flux is equal to E into V. And flux is equal to E. What is E? Electric field due to a point charge. Electric field due to at any point you see, the electric field due to the point charge is 1 upon 4 pi epsilon naught Q upon, and the distance is radius r square. And what about the area of the surface? 4 pi r square. R square or r square cancels. 4 pi cancels. You will get 1 upon epsilon naught times Q. So that is what actually the Gauss law is all about. But this is not a general information. This is especially for a spherical Gaussian surface, a spherical imaginary surface. Because this surface could be a bigger surface, smaller surface, a cuboidal surface, whatever it is. But here I have taken a spherical, but it is valid for any other surface. Because this formula, we can write it even in this form, E dot d, E dot ds. And the integral is a closed integral because there is no upper and lower limit, because if you start from the point and end in the same point, so it is a closed integral. So thus symbols are being used in NCERT, so you can use any of these symbols. So this is actually the standard form of Gauss law is this, the flux passing through a given surface is equal to Q upon epsilon naught. This is a full version of Gauss law. But in short, we can write it like this: flux is equal to Q upon epsilon naught. That's a short form of Gauss law. The flux passing through. So this is another formula for flux. This is an integral formula for flux, and this is a normal formula if electric field is everywhere same, and the figure has a special geometry. Even you can use this formula: phi is equal to E dot K. So this is a closed integral, means you have to start from the point and end at the same point. So that's all about Gauss law, but this Gauss law can be applied to find the electric field Without Gauss law, it may be a very long calculation using integration and all. But using Gauss law, that same derivation will be very, very small. So, before applying Gauss law, and there are some steps to follow when we apply Gauss law. The first and foremost thing is you have to find a suitable Gaussian surface. Maybe a spherical Gaussian surface, maybe a cylindrical Gaussian surface, maybe a cuboidal Gaussian surface, maybe a cubical Gaussian surface, whatever. But a closed Gaussian surface, an imaginary surface you have to go for, so that you can find the flux and also you can find the electric field intensity there. And the social Gaussian surface must be the angle area E dot, actually flux is equal to E dot A, so E or A must have either angle 0 degree or angle 90 degree or angle 180 degree, because these angles are very common to us. So we can easily find out the exact values. But if the angle is continuously changing, then integration will not be possible. Integration is not possible with more than one variable. So you should have only one variable with its maybe area. You are integrating the area. But if the theta is also variable, then it will be difficult. So theta must be constant or a particular value which is very known. So let's go with one example, application of Gauss law. So we are going to do 3 applications of Gauss law. And the first application of Gauss law is we're going to find the electric field intensity at any point due to an infinitely long uniformly charged straight conductor. Infinitely long uniformly charged straight conductor. So we have an infinitely long, so the conductor does not end here, it is infinitely long, but uniformly charged means it has a constant charge density. इसका हर जगह चार्ज डेंसिटी जो है सेम है. So uniformly distributed charge is here. And if we try to figurize the electric field lines, the electric field lines will be, it will be emerging through all possible directions in 3D in the space. So it has a cylindrical symmetry. It has a cylindrical symmetry. We can assume an imaginary Gaussian surface, which is a cylinder. So this is an imaginary Gaussian surface. Imaginary Gaussian surface. Gaussian surface is anyway always imaginary. A cylindrical, imaginary Gaussian surface of cylindrical shape. So if you want to find out electric field at this point, then you have to go for a small radius cylinder. If you want to find out at this point, so a bigger radius cylinder. But I'm going to find out, at this point, when I have made such a proper, suitable Gaussian surface, because the distance must be this only. This must be the distance, or you can write simply R. R is the distance, radius of the Gaussian surface. Actually, this R is the distance between. It's a perpendicular distance from the uniformly charged wire, charged conductor, to the point where we are finding the electric field intensity. So we have considered a Gaussian surface and we can apply the Gauss law. So Gauss law is Q upon epsilon naught. So how will you find the Q inside this? Q enclosed upon epsilon. What is the Q enclosed here? Inside this cylinder. So in order to find the Q enclosed, there are infinitely many charges, so we go for a concept called linear charge density. Linear charge density is equal to, symbolized by lambda, is equal to the total charge divided by length. So charge upon charge per unit length. So 1 centimeter पे या 1 meter length पे कितनी charges present है. So it is infinitely long. तो पूरी चार्ज को कैलकुलेट करना इम्पॉसिबल बात हो जाएगी. तो इसीलिए हम एक यूनिट लेंथ का चार्जेस को काउंट कर रहे हैं. सो एवरीवेयर द यूनिफॉर्मिटी इज द सेम. सो चार्ज इज यूनिफॉर्मली डिस्ट्रीब्यूटेड, यूनिफॉर्मली चार्ज्ड. सो इट इज सिंपल दैट वी कैन use this concept. Lambda is equal to Q into L. So Q is equal to how much? Lambda into L. So suppose the height of the imaginary cylinder Gaussian surface is h. Then what is the Q over here? Lambda into h. So phi is equal to Q lambda into h upon epsilon. Equation number 1. But by the definition, flux is equal to how much? E dot A, or integral form E dot dA, closed interval. And here are 3 surfaces which makes this total cylinder. So the cylinder is made up of 3 surfaces. One is upside surface, another one is a lower side cylindrical circular surface, and then we have a curved surface. So we'll be going for all these 3 surfaces. So let me put this as A1 and this area as A2 and this area as A3. A3 and A1 are the same. So E dot dA1 plus integral E dot dA2 plus integral E dot dA3. And the final answer, the dot product means cos theta. So what is the direction of area here? Direction of area is like this. But electric field line we have already. This is the direction of electric field line. So this is area, this is electric field line. The angle is 90 degree. So here integral E dA1 cos 90. And here E dA2 cos. Here is the area, curved surface area. It has outward direction, and the electric field also has same direction. So it is cos 0 plus, and the third one is also 90 degree because the area is in this direction and the electric field is in this direction. The angle is 90. Here the area is in this direction, electric field is in this direction. So area is, angle is 90 degree. But here the area also same direction and electric field is also same direction, so theta is 0 degree. So the final answer, we can put it like this. Flux is equal to zero plus E, and what is a curved surface area? 2 pi r h plus 0. So E is equal to E into 2 pi r h. That is equation number 2. And the comparing equation 1 and 2, what we get? Comparing equation 1 and 2. Comparing equation 1 and 2, you get E into 2 pi r h is equal epsilon naught, h cancel, or E is equal to lambda upon 2 pi epsilon naught r. That is the magnitude of electric field at any point which is at a distance r, and the direction I can write it like lambda is 2 pi epsilon naught r n cap, because it is perpendicular to the y. So n is actually a normal vector which is perpendicular. So that is our final answer for electric field at any point near a uniformly charged wire, infinitely long wire, yeah, infinitely long conductor. And even you can convert this formula in the standard form. In the standard form you can write it like, this is 2 pi epsilon naught, you can convert it into 4 pi. So you have to multiply it by 2 here and 2 there. So 2 lambda or 1 upon 4 pi epsilon naught into 2 lambda upon r. So here 1 upon r की हिसाब से इसका वेरिएशन हो रहा है. So that is the first application of Gauss law, and we found the electric field intensity at any point near a uniformly charged conductor, infinitely long conductor. So let's go for the second application of Gauss law. The second application of Gauss law is about an infinitely long sheet, but I cannot draw an infinitely long sheet on the board, so I am drawing a finite sheet which is uniformly charged. A uniformly charged infinitely long plane sheet. And I'm going to find electric field intensity at any point near. So if this is a sheet, a lot of charges are there, and somewhere here, what is electric field? So somewhere here, wherever, but near the sheet, what is the electric field intensity? So for that, I have to consider a Gaussian surface again. So here also I am going to use cylindrical, or even I can use cuboidal Gaussian surface, because the electric field again has this, and this side also electric field outward, because positive charge has always outward electric field. So suppose if I am going to draw a so the electric field is in this direction, here also electric field is in this direction, and in this direction there is no electric field, area is there. So here this area I will just put like A1, here A2, and this area is curved surface area is A3. So A3 and the electric field lines are at 90 degrees, so theta is 90 degree here, but A1 and electric field line theta is 0 degree. For A2 also electric field line theta is 0 degree. And what is a flex? The flex is again simple, E dot A integral dA, and you can write it like this: integral E dot dA1 plus integral E dot dA2 plus integral E dot dA3, and the total. What is the totality here? Flex is equal to E dot dA1, so integral E dot dA1 cos 0, integral E dot dA2 cos 0, or integral E dA3 cos 90. So this one is, so let this area I am going to put A1 is equal to A2 is equal to pi r square, I am putting, but the r has no importance here, because I can make any bigger or smaller cylindrical surface. It does not mean anything because at this point I am going to find out electric field. So at this point it has no meaning of radius, it has only the meaning of the distance here. So EA plus EA plus 0. So I get 2EA, that is a flux. But by Gauss law, what is the flux? By Gauss law, the flux is Q enclosed upon epsilon naught. And what is the Q enclosed here? What is the Q enclosed here? So here is a surface charge area. So surface charge density, and the surface charge density sigma is equal to charge divided by area. Linear charge density lambda is equal to charge upon length. So charge by area. So here Q is equal to sigma into area. I can put it sigma into area upon epsilon, where sigma is surface charge density. So these two equations, if I comparing these two equations, what is the final answer? We'll wrap it off. The final answer will be 2EA is equal to sigma A upon epsilon naught, and A cancels. E is equal to 2 sigma upon epsilon. So you get an electric field is equal to 2 sigma upon epsilon. Again, you can put here n cap. 2 will be in the denominator. So this is sigma upon 2 epsilon naught. A half sigma upon epsilon naught is the electric field intensity due to a plane sheet, infinitely long plane sheet, at any point near its whereabouts. So that is the second application. And one of the important factors here, electric field depends only on charge density. It does not depend on how far away we are taking. So almost near about any point, the electric field intensity is independent of the distance. That's why here we see. Okay, let's go for the last. Topic, that is application of Gauss law. The third one is a spherical object or a spherical conductor which is uniformly charged. Uniformly charged hollow sphere. Hollow spherical shell. So a spherical shell is there. Which is uniformly charged. A very fine thickness it has. So it is uniformly charged. And here also you can go for charge density, but even you can go for the entire total charge also. What is the electric field intensity inside the hollow spherical shell? And what is the electric field intensity outside the hollow spherical shell? So this is a given diagram, a given thing. So here hollow spherical shell is not an imaginary Gaussian surface. It is an actual surface which has actual charges on it, and it is a uniformly charged hollow spherical shell. And thus I am going to find first inside the shell what is the electric field intensity. So for that I have to draw a Gaussian surface, and this Gaussian surface is also, so let me assign some variables. For the actual sphere the radius is capital R, and for the Gaussian surface the radius is imaginary surface. So imagine a spherical Gaussian surface because both have a symmetry. Gaussian surface of radius small letter r. So here r is less than r. In this, what is flux? Flux is equal to E into A. And what by Gauss law, what is flux? By Gauss law, what is flex? By Gauss law, the flex is Q enclosed upon epsilon naught, or is equal to Q enclosed is how much? 0 upon epsilon naught is equal to how much? 0, because there is no charge inside this. Every charge is on the surface because it is hollow spherical shape. So here we see, comparing this both equation, E into A must be equal to 0, and we know that the area is not equal to 0. Therefore, what is 0? Therefore, electric field intensity inside a spherical shell, even though it is fully charged, it is 0. And the second part is outside the shell. So outside the shell means R is greater than R. For that you can make again a, okay, this is the shell, uniformly charged, and I am going to imagine a cylindrical surface, Gaussian surface, and which has a radius greater than the radius of the original sphere, the spherical shell. So then, what is the electric field intensity inside? So by definition, by formula, we know that the electric field intensity is equal to, flux is equal to E dot A, or flux is equal to E into the total surface is what? 4 pi R square, or cos 0, because the area direction is this way and the positive charge direction is also this way. So the theta is how much? 0. So flux is equal to E into 4 pi R square, equation number 1. By Gauss law, what is that? Flux is equal to Q enclosed upon epsilon. And Q enclosed, you can even keep it like Q upon epsilon. The total charge is Q. And even you can go for Q is equal to sigma into A, because sigma is equal to Q upon A. So here you got equation, comparing equation 1 and 2. E into 4 pi R square is equal to Q upon epsilon naught, or E is equal to 1 upon 4 pi epsilon naught. So Q upon R square. That's a proper way to write. Q upon 4 pi R square epsilon naught. So this is the same as a point charge. For a point charge, the formula is the same, 1 upon 4 pi epsilon Q upon R square. So it means that this spherical surface, the spherical shell, the charges on the spherical shell now is acting like a point charge, which is situated at the center of the spherical shell. But inside the shell there is no electric field, but outside the shell the electric field is this. And you can even convert this Q into sigma into E. And here the radius is capital R, because the radius is small letter r, but if you go for this Q, the radius will be capital letter R. Sigma is equal to charge upon area, and sigma is equal to charge upon 4 pi R square, because the charge is on the original sphere, not on the imaginary one. So this is the original one, and the charge is on the original one, so the radius will be the original one, 4 pi R square. So if you put Q is equal to sigma into 4 pi R square, 4 pi will cancel, and you will get another formula, electric field is equal to 1 upon 4 pi epsilon naught, or sigma into 4 pi R square upon R square, the 4 pi cancel. So sigma upon epsilon naught into R square by R square. That is another form of this formula. So today what we have learned is the major 3 applications of Gauss law. The number 1 was, for an infinitely long straight conductor, electric field is, how much is electric field? For an infinitely long straight conductor, electric field is equal to what? lambda upon 2 pi epsilon naught r n cap, where it depends on r and lambda. And for a infinitely long plane sheet, uniformly charged plane sheet, for that it was half sigma upon epsilon naught. Yeah, sigma upon 2 epsilon naught n cap. And here also you have this same direction n cap, but the value is 1 upon 4 pi epsilon naught q upon r square n cap, or the value is sigma upon epsilon naught r square upon r square n cap, in terms of charge density and in terms of the total charge on the spherical shell. So with this, the chapter gets over. The entire topics of the chapter is over. So the whole chapter revision, and in the next module I will be giving you few questions which came in the examination previous years, so that you can again thoroughly revise this chapter. So learn all these derivations, this 3 derivation, and the torque 1 derivation, and then again the 2 derivations of electric field on the dipole. So learn all these derivations and do the concepts. We have done now up to 14 questions. So here you have to do from question number 15, 1.15 to 1.24. This will entirely cover the whole chapter, and this chapter will have one more module, module number 4. In that we will discuss some previous year's questions. Okay, that's all.